Hello everyone. Welcome to our lecture number 17. I hope you're all doing well. Today in this lecture, I'm going to talk about different types of power cycles in the beginning, and then we're going to solve an example about Brayton power cycle. And all these materials will be about chapter 9 of the textbook. So in the beginning, let's define a power cycle. Okay, so as we know, a cycle consists of different processes or different paths. For instance, here we can see the cycle 1, 2, 3, 4, 1. This is a cycle, and cycle in different cycles, the initial and final states will be 1 point. So it's gonna end up at the same or same initial point that it started. Okay, so here we have four different processes: 1 to 2, 2 to 3, 3 to 4, and 4 to 1. And each of these numbers are one state or one checkpoint, for instance. So, and then the power part means that in total, when we go through this cycle, or when this cycle is happening in a device, the outlet would be some sort of power. For instance, it might be shaft power or propulsion power, which is kinetic energy, or different types of powers, right? So when we call something as like power cycle, so we expect that the output would be something valuable, something that we can do something with that. So when the cycle is happening, so we would have a system, right? A system that the content of that system um, is going through the processes and the cycle. So let's imagine that we have this open system here, and we have different types of energy flux inlets. It might be heat, so we add heat to the system, or we do work on the system, and we expect to have the outlets of energy rates as well. It might be again different types of energy. Yes, different types of energies. It might be heat or work, right? So in this case, up to now, so we know like that the cycle. What do we mean by the cycle? And depending on what sort of combination of all these processes we gather together to make the cycle, we will end up with different cycles, right? Let's say we want process 1, 2 to be isentropic process, 2 to 3 to be pressure constant, 3 to 1, 3 to 4 to be like a, I don't know, like temperature constant. So all these specific processes might be something: isentropic, adiabatic, constant pressure, constant temperature, blah, blah, blah. And then if we focus on the system material, what is inside our system, what is the working fluid, we can divide different types of cycles, power cycles, into categories. So if we have air, or let's say a mixture of air and the fuel, and then like it combusts and then it goes to the turbine or the compressor or whatever, then we will have different types of cycles, and we call that gas power cycle. On the other side, on the right side, if we have something that evaporates and we deal with different um, statuses or different phases of the material, like liquid and vapor both together, then that would be a vapor power cycle. For example, we might work with like R134A or water. So we might have different phases of H2O or R134A. So in the gas power cycle, we can have Otto cycle, diesel, and dual cycle, which be a combination of diesel and Otto somehow. And in all these three different gas power cycles, the system would be some sort of closed system, because the process would happen in just a piston cylinder device. And as soon as the fuel, the mixture gets into the system, into the cylinder piston device, then it will be trapped there, and then the combustion, uh, compression, and expansion or whatever, then they will happen. And everything would be closed. All the inlet and outlets would be closed. So that would be a closed system. And we have open systems as well, but in different cycles, which are called Brayton. Um, that we use this cycle in aircraft, engines, and in electric power plants for electric to generate electric power, right? And the other cycle is jet propulsion, which is something similar to this air. Is actually it's the same thing, and it's similar to jet propulsion. So Brayton and jet propulsion are similar, but with different differences that I'm not gonna talk about them now here. And these systems would be open because we have a continuous flow of the fluid, right? And on the other side, we have vapor power cycle, which the only cycle that we're gonna learn is the Rankine. So in this lecture, I'm gonna talk about Brayton. Okay, and you might have heard of Carnot cycle. That is something else. That is the most efficient cycle, or in other words, that is the most efficient combination of different processes that gives us like the most efficiency, right? The best efficiency. So that's the combination of different processes, different types of processes that gives us the best efficiency. And that's kind of like an ideal model for a cycle. And also, it's defined between two specified temperature limits. But anyway, so we are gonna solve an example about Brayton cycle, right? So let me give you more information about Brayton cycle. Brayton cycle is the ideal cycle for gas turbine engines, as I addressed before, like in aircrafts or in electric power plants. So uh, again, let me repeat this. That so we are talking about a power cycle. So we expect to like we have some sort of like a combination of devices like heat exchanger, compressor, turbine, and we give heat, right? We add heat, and we do work in the compressor on the system. We add heat in the heat exchanger, and we expect the turbine to give us uh, work, right? The output. So in each of these devices, in each of these subsystems, compressor, turbine, and heat exchanger, there is a process going on, a path going on. Like remember 1 to 2, 2 to 3, all this stuff? Yes. So in this cycle, it is a combination of, so 1 to 2, state 1 to state 2 is an isentropic compression. The next process that starts or happens right after this one would be 2 to 3, state 2 to state 3, which is a constant pressure heat addition, and it happens inside a heat exchanger. So meanwhile that we are adding the heat to the system, pressure would be remains constant. And then state 3 to state 4, which is again isentropic expansion. These two isentropic processes, the compression happens in the compressor, and this one occurs in the turbine. And then this cycle should end up at the same status as it started, which is point 1, and that would be again a constant pressure, but here it's heat rejection. So we absorb heat from the system. And again, it happens in the heat exchanger. And if I draw, let me draw the system for you, like the devices, the parts. Here is my compressor, and that would be a schematic figure. So in compressor, we know that we kind of like shrink the flow, like squeeze the flow. So when it enters from here, it should go out from there, right? Because like the shape is like it diverges, right? Anyway, so let me. Okay, so now this is gonna be connected to a heat exchanger, right? And then the outlet would go to the turbine, and here the gas expands, right? So the turbine, it like um, it expands, and then the outlet goes again to another heat exchanger to reject the excess heat. So here's my compressor, here's my turbine, and heat exchanger, heat exchanger. Here is, and the process goes this way. This is the direction. And let me define the different status, different checkpoints. Here is point 1. Then after the compressor would be point 2, and also which is before the heat exchanger. After heat exchanger, before the turbine, is point 3, and likewise here, point 4. So the turbine, in most of the cases, the turbine and compressor are installed on the same shaft. So here's my shaft that connects the compressor and the turbine. And let's say here is the outlet. So I expect to get work, the net work, out of this shaft. So that would be like shaft work. And it's some sort of like W dot net that it's coming out of the whole combination. In this section here, we reject the heat, and in the other heat exchanger, we add heat. Here heat goes in and then goes out, and then here's the work that I get. Okay, please check lecture 19, page 1. Thanks. And also about different about different power cycles, please check lecture 16. Okay, great. Now let's draw the diagrams. In most of the cases, we draw TS, temperature versus entropy, right? Temperature versus entropy. And all these processes might happen ideally or actually, right? The ideal process is like the best. Like, you remember I was talking about efficiency of compressor or turbine, how we define that. I'm going to talk about this here again. So if we, in an ideal world, a compressor would be perfect, right? No heat loss, like nothing. Everything is isentropic, entropy is constant. It's perfect. So in this ideal case, compressor and turbine would remain on an isentropic compression and isentropic expansion respectively, right? Then from point 1 to point 2 we had 1 to 2 we are passing through the compressor, and we expect to have a, an isentropic process. So entropy remains constant. In the other process, so sorry, in the other, so here is like point 1 and point 2. Now I want to talk about the other point 2 to 3. Okay, let me move the whole thing. Here is 1 to 2. Then the process 2 to 3 occurs in heat exchanger when we add heat, so temperature goes up, but pressure remains constant. So we need to draw a constant pressure path, and we're gonna stay on this curve because pressure is constant, and we end up at point 3. And here pressure is constant, and we are gonna add heat q dot in. Everything is in um, rates, so it's like energy kilojoule per kilogram per time. And then so we are at point 3. Point 3 is the beginning of the turbine, and we go through turbine and we end up at point 4. And we are in an ideal world, so we expect the process to be isentropic, entropy should be constant. Therefore that would be again like in straight vertical line, and we end up at point 4. Entropy is constant. And point 4 to point 1 would be another constant pressure process, right? And on this line here, on this curve, pressure is constant again. Oh, and we absorb heat, so Q goes out. Q dot out. Point 1, 2, 3, 4. And here is the direction. And these are vertical at 2 specific entropies. This is the ideal case in the ideal world. But then the question would be like, so what if we are actually like, what about our actual life? What happens in our life when a compressor or turbine works? How do they work? Please check here. Please check page 2 of lecture note 19. In the ideal world, we're going to have the same thing but with different changes. So process 1 to 2 was an isentropic process in an ideal world, but in actual life, in nature, that's not going to be isentropic. So entropy would increase, and we know that in processes entropy always increases. So if an isentropic process would look like that, straight line, entropy constant, then our process 1 to 2 would not be straight. That would be like a curve or line. So from point 1 to point 2, entropy increases. And we said that in the heat exchanger we expect the pressure to be constant, but it's not going to be constant. That's going to drop because of all those internal pipes, valves, knees and stuff. So pressure is going to drop. So we're going to go off that curve and end up at a lower pressure, like that. And again, if it was the next process, if it was isentropic, we expect that to be like a straight vertical line, but it's not. The entropy is going to increase. So we go off like that. Entropy increases. So from here, this entropy, we end up at that entropy. Here, from entropy, here, we end up at that. So entropy increases. And again, the pressure should remain constant, but it's not going to be constant. It drops, right? So let's say, sorry, it's so let me connect these two guys first. It's difficult to draw. And then pressure is gonna drop, right? So that would be like that. No, no, I don't like it. Let's say, oh, let's say this was my curve. And here's the other one. Okay. This is what I expect. I'm sorry about that. This is what I expect. Yes. So this is a constant pressure, and this curve as well is a constant pressure. But we started, so here's point 1, point 2s as if it was isentropic, but we end up at point 2 actual, and then we went up to point 3. But if the pressure was constant, this curve would look like that, like on this dashed line, and it would finish there. But the pressure dropped, so I'm gonna end up at a lower curve. Then there's another process in the turbine, and we expect that to, oh my god, sorry, and we expect that to, if it was isentropic, we expect that to end up there, so 4.4 s, but it's not. It's gonna end up there, which is the actual point 4, right? It's difficult to draw, on this surface tablet. Oh my god. Whew. And then, so here's a constant pressure process. So from here, we expect this curve to be like, if the pressure was constant, to be like something like that and end up there, but we drop. So this is the actual process. This is the actual point 1. So, and this is the direction. We add heat here and reject there. Here is process 1, 2 happens in the compressor, and 3 to 4 in the turbine. Okay, now how do I define, again, the efficiencies? Please check 19 page 4. And then the efficiencies would be like this. the efficiency for compressor is, so an ideal compressor requires less work than comparing to an actual compressor, because an ideal compressor is like a better compressor, right? It's like, so it's like more efficient, so it needs less work to gives us the same pressure ratio. So let's say W isentropic ideal divided by W actual, right? And actually these are little w, so it's per mass. W, sorry, isentropic divided by W actual. And in terms of enthalpies, that would be, so in compressor, the compressor, inside the compressor we have process 1 to 2, so the isentropic work is H at this point 2S minus H1, the difference between enthalpies, divided by now actual 2A minus H1, the difference in enthalpies when the process happens actually. And then the efficiency of the turbine would be, now a better turbine in an ideal world gives us more work, so it's going to be larger than an ideal one, so it goes in denominator, Ws divided by Wa equals, so in the actual process look like 3 to 4A, that would be H4A minus H3. Well, actually this is negative, so let me switch them. So that would be H3 minus H4A, because the enthalpy at point 3 is more than 4 at this point. Divided by isentropic process, 3 to 4S. So that would be H3 minus H4S. So in the turbine, enthalpy drops, decreases, because the material, like steam or the gas, loses the enthalpy, loses the energy, because it's doing work on an external shaft. And the corresponding pages would be for compressor, here 15 page 5 and 15 page 4. Now the example. That was the introduction. So let me see how much times. Oh my god, 30 minutes. Okay, now let's go to the example. Our example is lecture material, lecture, sorry, lecture examples, this one, first one. And I'm gonna read that for you just to keep it in mind that what's the story. Okay. I'm sorry, this lecture might be long because we're going to talk about a cycle with different processes. It says a gas turbine. Okay, gas turbine material is the working fluid is gas. It's gas and like fuel. It's not vapor. It's not steam. We are not going to talk about saturation and stuff. So keep in mind from the beginning that okay, it's gas. It's a gas, ideal gas probably. A gas turbine power plant operates on the simple Brayton cycle with air. Okay, so the material is given air as a working fluid and delivers 32 megawatt of power. Okay, so the net power coming out of the shaft would be 32 megawatt. It says the minimum and maximum temperatures in the cycle are 310 and 900 Kelvin. Let's see the curve, the diagram. So here, the lowest or the minimum temperature, here's temperature, right? Temperature versus entropy. Temperature versus entropy. The minimum temperature would be at point 1. And it says the maximum pressure, which should be here, zero point 0.3, because it's going to be like, see, this is the largest value. It's 900 Kelvin, okay? And the pressure of air at the compressor exit is 8 times the value at the compressor inlet. So in the compressor, pressure goes up 8 times larger, and in the turbine, assuming that the process 2 to 3 here, 2 to 3 and 4 to 1 are constant pressure, so from point 1 to point 2 pressure goes up 8 times larger, and from point 3 to point 4 drops 8 times less. Then it says assuming an isentropic efficiency of 80% for the compressor and 86% for the turbine. Determine the mass flow rate of air through the cycle. Important note: account for the variation of specific heats with temperature, which means that, okay, you can assume that air is an ideal gas, but when you are talking about enthalpies in the process as temperature changes, you cannot say like, okay, delta H equals Cp times delta T. Why? Because the specific heats are not constant. So you cannot linearly multiply Cp times delta T. We need to go to the tables and we need to find enthalpies separately at different checkpoints, at different states, point 2, point 3, point 1, point 4. Okay? We cannot use those formulas, which says delta H equals Cp times delta T, or for internal energy, delta U equals Cv times delta T. We cannot use those. Those are for constant specific heats, not variation of specific heats. Okay? And we have isentropic efficiency for compressor and turbine, and nothing is mentioned about heat exchangers. Therefore, it's safe to assume that process 2 to 3 and 4 to 1 were or are in a constant pressure process. So the first step is system. What is the system? So in a cycle, we're dealing with different devices, like compressor, turbine, heat exchangers. So we're gonna have different subsystems, right? So multiple subsystems, which means, compressor, heat exchangers, additional, and addition and rejection. In the addition heat exchanger, we add heat comes into the system, and in a rejection heat exchanger, the system loses the heat, right? And we have the turbine. So we have 4 subsystems, okay? And the question is, find the mass flow rate for this cycle. How much is it? And we can assume that air is an ideal gas because we need to use the tables. So it's asking for m dot. And if you go a little bit deep in detail about this question, the only thing beside pressure and temperatures, pressure ratio, temperatures, and isentropic efficiencies, there is just one parameter given, which is the W dot out, how much of power we get. Okay, And so I have the work, I mean W net. So I have the work and the unit. So let me see. I have the work. So is it possible to make it write it this way that okay, m dot with the unit of kilogram per second equals W net out, right? The net power, the outlet power, and in the unit of kilowatt. If I divide this by the specific work, if you take a look at all those tables, property tables, enthalpy and internal energy, everything is per mass, per kilogram. Is kilojoule per kilogram for all of them. So if I divide these by the little w, which is specific work, which is like kilojoule per kilogram, then what would be the unit? The unit here is kilojoule per second, which is watt, kilowatt, divided by kilojoule per kilogram, and kilojoule cancels, and then I'll end up with kilogram per second. This is exactly what I want. So the specific work is per mass and work is per time, both energy per time and energy per mass. So if I divide these two parameters, I'll end up with the mass flow rate. This is what we are gonna do. On the denominator here, W net out, we know it's 32 megawatt. And in the denominator, we need to solve for it. We need to solve for little w net out. And everything is gonna be, from now on, everything is gonna be per mass, per kilogram, all the units. Now the question reforms to what is W net out in the unit of kilojoule per kilogram. What's that? This W, it's the net, it's the total work, which means that's going to be how much of work is produced by turbine minus how much of work is consumed by compressor, right? Now I need to divide the whole solution, the whole process into two sections. Solve for W turbine out and then solve for W compressor in. In the compressor we add work, W in turbine we get the work, W out. Then I need to separately solve for these works and then put it back there, solve this guy, and then put this in this equation here up there, and then find for m dot. That's the whole process that you're gonna do. And before this, just to make it more clear for ourselves, let's draw the diagram. Process 1 to 2 is inside the compressor, and it's not isentropic because the efficiency is not 1, it's not 100%. For compressor it's 80%. So that would look like this, and the isentropic path is that. Then pressure is constant because nothing is mentioned in the question, so we assume, just to make the life easier, that pressure remains constant in the heat exchanger. And once again, now we are in the turbine, and in the turbine we assume that is how the isentropic process look like, the curve, but now the entropy increases, so it ends up at a higher entropy. And again, we assume that pressure is constant in the second heat exchanger when the heat is rejected. Then we remain on this curve. So here's the path. Point 1, point 2. Oh, sorry. Point 1. Let me write this in black. Point 1, point 2 actual, but if it was isentropic, we would end up at there, 2s, at the same pressure. Then we go up to point 3 because now we are adding the heat, q dot in, and then after the turbine, as we pass through the turbine, we're gonna end up there, point 4 actual. But if it was isentropic, then we would be here, 4s, and then back to point 1. So the cycle completes and repeats. Here is the direction. Okay, awesome, awesome. So first, I'm gonna solve for this guy. So now you know the procedure. Solve for these two parameters, put it back in this equation, solve the net work per mass, and then put it back there and find m dot. So now, how much is WC in? This is the question. To be able to find the work consumed by the compressor, we can, based on the tables, we can solve like the enthalpy, solve for enthalpies. If the process 1 to 2, here's the process. So when we are now inside the compressor, so our subsystem is the compressor. Is it right? I got confused. Compressor, right? Yeah. So the subsystem is the compressor, and the process is point 1 to point 2, but it's point 2a actually, right? So all these enthalpies that we can solve based on the equation, based on the tables, because now we're going to talk about variation of specific heat. So we need to use the tables. Here's a table that we use, A17 in the textbook, and it talks about enthalpy and internal energy and entropy if the process 1 to 2 was isentropic. So if we still want to use the tables, we need somehow to include the efficiency. So we need to say that, okay, I am looking for the actual work of the compressor. Okay, let me get rid of in, and instead of that, write the actual work for the compressor. I know that the efficiency for the compressor is defined this way. The work, isentropic work for compressor divided by actual work, because the actual is more than the isentropic ideal case. And here we have H from point 1 to point either 2s or 2a. Isentropic, so 2s minus H1, actual, subscription of A, H2a minus H1. So the difference between the enthalpies between point 1 and point 2 in two cases, actual case or isentropic case. And that would be the entropy. Oh, sorry, the efficiency. I know that this is 80%. And like using the summary table and the property tables, we can solve for this guy. We can solve for isentropic case. We can. I'll show you. This is fine. We can. But still, we're looking for the actual work. So okay. So if I use the tables and if I solve for WS compressor, put it there, then I can solve for WAC. Easy. So how do we do that? Okay, now I need to solve for WSC, isentropic work. S means isentropic work. Then that would be the denominator here, H2S minus H1. And okay, so at point 1, and let me write, I forgot, oh my god, to write the table. So I have 4 points, right? Point 1, point 2, point 3, and 4. Okay, I know that the minimum temperature, which should be point 1, because see, this is stable, this axis is stable, is temperature. So the minimum one is here and the maximum is there. So point 1 and point 3, we know the temperatures. So T1 is 310 Kelvin and T3 is 900 Kelvin. Okay. And we know the pressure ratio in the compressor and in the turbine. Once again, we assume that in the heat exchangers, pressure remains constant. Therefore, we know that P after the compressor at the outlet, it is 8 times larger than the inlet. So P2 is 8 times P1. And about the turbine, we know that when we passes through the turbine, pressure drops 8 times. So P4 would be 1/8 of P3. P3 is before the turbine at the inlet, P4 is after, right? And so it's just a ratio. The ratio is 8. And the ratio means here is for compressor, here is for turbine. Means that like a before and after. This is the ratio. And we have the efficiencies. That's all we know. So at point 1, material is air. And we need to use table A17. Therefore, and I'm looking for H1 and H2S to find WSC, put it there, and find WAC, the actual. Now, what is H1? How much is H1? At this temperature, 310 Kelvin. That is gonna be, according to my table, A17. It says at this temperature, that's gonna be your enthalpy, and PR is that. I'm gonna tell you why do I need PR, and what is PR, and also VR. But let's, where is it? Okay, so H1 based on that table would be 310.24 kilojoule per kilogram. And also PR1 at the same temperature is gonna be 1.5546. Okay, now according to variation of specific heats with temperature, there's a trick. And the trick is, well, you can check this lecture 14, page 6. Okay. And what's the trick? The trick is that, well, I mean, like it's a relation that it says, Okay, you want, here we are talking about process 1. Everything now, from now on, everything, see, we assume everything is isentropic. So if in process 1 to 2s, isentropic, we want to find the enthalpy at point 2, point 2s, isentropic. But on the other side, the specific heat is not constant. So we cannot use Cp times delta T. So the table helps us. It says, well, so you're looking for a link between point 1 and point 2s, right? Because all I know is just the temperature at point 1, and that's it. And sorry, and also the pressure ratio. I know, see, let's go back there. I know that at point 1, the temperature is that, and I know that the pressure ratio is 8. Okay? Now here, there's the relation that it says, do you know the pressure ratio? Yes. Okay. So P2 divided by P1, I know it's 8. After the compressor, it's 8 times larger. And are you assuming that the process was isentropic? Yes, of course. Yes, I do. Here, I assumed. Then I can give you the link. Then P in between point 1 and point 2. Then I can give you this relative specific relative pressure, which is PR2 and PR1, or I can give you a relation between specific volumes if you are still assuming it's isentropic. Yes, of course, I'm assuming. Okay, then I can give you, here's a table. What table says? I can give you R VR2 divided by VR1. And all these relative properties, VR and PR, are given in the table. See, I showed you before. Here PR, all that column, and VR. And likewise in these columns. That's good, because here I have the pressure ratio. I know that in the process 1 to 2s, P2 over P1, or let's say P2 is 8 times P1. So P2 over P1, same pressure ratio in an isentropic process, is 8. Okay? And that is gonna equal to PR2 divided by PR1. Okay? And at point 1, based on the table, I know that at this pressure, this is PR1, so I can find PR2. It would be 8 times PR1, which is this. So by use of that link, this portion, we found PR2, 12.44. But what are we looking for? We were looking for H1 that we got here. And then we were looking for H2S as if the process 1 to 2 was isentropic. It's not, because the efficiency is not 100%. Then I have the PR2, and if I go back to my table, at that PR2, which is about like 12.44, so this column, the third one, is the PRs. So we will be between this guy and this guy. And if I interpolate, because the PR2 is 12.44, so we are in between. The second column, this one, are the enthalpies, and I'm looking for enthalpy. So then my enthalpy would be something in between these two values, right? So if I just do a simple interpolation, I can find for H2S. Interpolation means, let me just write it here small, that it says if you have A, B, C in one column and A, B, C in the other, and you're looking for this guy, and you have this guy, then B minus A divided by C minus A equals capital B minus A divided by C minus A. Linear interpolation. That's it. I'm gonna do the same thing here in between those values that I showed you before. So I'm gonna have minus 11.86 divided by 12.66 minus 11.86 equals now the enthalpies. I'm looking for H2S if the process was isentropic minus that enthalpy 65.4 minus 1, 2, 3, done. Therefore, H2S would be 562.58 kilojoule per kilogram. Now I can solve WS, the isentropic work for compressor, which was H2S minus H1. H2S is right there. And H1, based on the table, was this. So W, the isentropic work for turbine, for a compressor is 252.3 kilojoule per kilogram. Now, let me go through what am I doing? So, we solved for this guy. Isentropic work for compressor. Now I can put it there, isentropic work for the compressor, and I have the efficiency, so I can find the actual work for the compressor. Therefore, the actual work for a compressor equals isentropic work divided by the efficiency. Just change those two, exchange them. So 252.3 kilojoule per kilogram divided by 80% would be kilojoule per kilogram. Great, 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 great. So I found the actual work for the compressor. There you go. Why am I doing this? Let's go further back. A little bit more back, I mean. Here, I was looking for this guy, and I found it. The actual work for the compressor going in. This is, and this both are actual. Then I can find, again, the actual work, net work, and divide it, put it there in the denominator, and then find m dot. That's all I'm gonna do. And I'm gonna do the same process for this guy now for turbine. Because if you look at the table, I know the temperature here and I know the pressure ratio. I'm gonna do the exact same process, but just with different formulation, because now it's gonna be about the turbine. So what is the turbine actual work, right? And the system is, the subsystem is turbine, and the process is 3, 2, 4 actual. We should use the efficiency because the efficiency relates the actual and isentropic works. And for turbine, it would be the actual work divided by the isentropic work because in the denominator is a larger value, it's isentropic, and ideal turbine gives us more work. And in terms of enthalpies, it would be H3 minus H4S. Sorry, it's actual. A and H3 minus H4S. I'm sorry that it's. Oh my god, we passed 1 hour. Okay. So now I'm looking for this guy and I'm gonna solve for that. I'm gonna assume that the process was 324S isentropic, and I'm gonna say that okay, W isentropic for turbine is H3 minus H4S, and now I need these two guys. I know that at point 3 I have the temperature, so I can say, well, I'm talking about air, ideal gas, and I can use table A17. Then at point 3 I can get that H3 is 932.93. What's the unit? Energy per mass. Everything is per mass because I'm using the tables. And since I know that I would need PR3 at the same temperature, then I'm gonna save time and write it now. So I have these guys, and again, back to page 6 of lecture note number 14. I know that I'm assuming that process 3 to 4S it was isentropic, so P4, look at the diagram. We are on the red curve dashed lines. We assume it's isentropic, as we did here. We assumed it was isentropic, we found H, and then we used the entropy, and we found actual work. We're going to do the same thing here. We assume it's isentropic, we find the isentropic work, and then we use the efficiency and we solve for actual work. Then we know that P4 divided by P3 isentropically equals the relation between relative pressures. Here we don't have anything about the volumes, the specific volumes, so we're going to use this ratio. And I know that after the turbine pressure is 8 times smaller, so this would be 1 over 8, right? Because point 3 is before the turbine, point 4 is after the turbine. After the turbine, the pressure dropped, so it's 1/8 equals PR4 divided by PR3. I have this guy, so I can find PR4, which is 9.411. 9.4. Keep it in mind. 9.4. 9.4, 9.4, 9.4, 9.4, 9.4, PR 9.4. Here, this column 9.4, 9.4, 9.4, 9.4, not there. Between these two guys. So the enthalpy would be between these two guys. Once again, I need to do the interpolation, right? This column is PR, and our PR at point 4S is in between these guys. So the H at 4S would be between these guys. T at 4S would be in between. All these values would be in between these two guys. Interpolation. Wait. Yes. looking for H4S. Divided by, so the enthalpy at point 4, as if the process 3 to 4 was happening isentropically, is gonna be 519.3 kilojoule per kilogram. Now I know that what the enthalpy is at point 4s, this guy, doop, and doop. So I can find the isentropic work of the turbine. For 13.6 kilojoule per kilogram. We are about to solve it. Now we have the isentropic work, but we are looking for actual work. So we need to use the efficiency. And efficiency is here. I'm looking for this guy, which would be efficiency times isentropic work. I'm looking for the actual work for turbine to subtract that from the actual work for compressor, then I get the net work. Now 86% is the efficiency, and the isentropic work is this, which would be 355.7 kilojoule per kilogram. Great. Now, why are we doing all this stuff? Because we are looking for the net work coming out of, sorry, of course the turbine does more work, of course. So the actual, because we are doing all this to get a net positive network, right? This, the whole point of this process is this: actual work for turbine minus actual work for compressor. So 355.7 minus 315.4, which would be 40.3 kilojoule per kilogram. So if I use 1 kilogram of air, the total work coming out is that. And I know that the power is, I'm looking for m dot. It was like 1 hour ago. W net out divided by little w net out. And I know that the power, total power is 32,000, it's mega, right? Kilojoule per second. And I know that this cycle produces this much of energy per 1 kilogram. So these two guys, bye-bye. Then m dot of the cycle would be 794 kilogram per second. So in 1 second we are using that much of air. This is the answer. Thank you so much for listening to this lecture. I'm sorry that it was kind of long.